Let's look at a couple examples of three-dimensional vector fields. This first one, notice, is defined as fxyz is I plus k. Just to inspect this a little bit further, we're talking about this vector field. This is a constant vector field because the component functions of the vector field are all constant. So in terms of the letters p, q, and r, the p function is 1, the q function is 0, and the r function is 1. It's a perfectly good vector field. It's just that the coordinates don't change with x, y, and z. So what this is saying is at every single point in 3 space, we attach the vector 1, 0, 1 to it. So you can, try and plot a few of these. The 2-dimensional vector fields are hard enough to do by hand. The 3-dimensional are quite tricky. But anyway, at the origin, I've got this vector out 1, up 1 attached. At some other point in 3 dimensions, I've got that same vector attached, and so on. So I could just draw as many of these vectors as I can. It's the same vector 1, 0, 1 getting attached to every single point in 3 dimensions. Wolfram Alpha doesn't appear to have a great way to plot 3-dimensional vector fields, so I'm using Grapher. If you put a delta symbol and then XYZ or XY if you're doing a 2-dimensional one, and then the components of your vector field in a stacked vector over here, then it will graph the vector field for you. So this is Grapher on Mac. The default arrow style has these gigantic arrowheads, which sometimes can be distracting, I think. But I think you can mess around with the sizes, and that sometimes helps a little bit. But anyway, this gives you some visual of the 3-dimensional flow of this vector field. You see the vector 1, 0, 1 attached at every single point in 3 dimensions. Okay, now let's look at a vector field that is constructed from a multivariate function. So as mentioned before, if you have a 2-variable function and you compute its gradient, then you are computing a vector field associated with that function. So the inputs of this vector field are the domain points of the function f, and the outputs are these vectors. Here you can see they depend on the input values. And that vector tells us something about the function. The vector points in the direction of steepest slope of the surface, and its magnitude is that steepest slope. So let's plot a couple points by hand, and then I'm going to go to Grapher again. And since I'm talking about a gradient vector field, I can interpret what that vector field is telling me about the original surface. Okay, so at the origin, I'm going to get a 0, 0 vector. At the point, let's say 1, 0, I get the vector 2, 0, like this. At the point 0, 1, I get 0, 2. At the point, let's say -1, -1, I get the vector -2, -2. This. Okay, so that's some image of the vector field. I definitely want to plot a lot more if I really wanted to get a feel for the vector field. So now let's move over to Grapher. I've got 2 things plotted here. The first is a contour map of the 2-variable function fxy. So if you just put in x squared plus y squared into the 2D plotter, it will put just the contour map of the function. So we're used to looking at these. It's just that the colors help me understand a little bit more about the z value in place. So we know this just to be a simple paraboloid that is 0 height at the origin and then increasing as you go outwards. So this is just a really nice picture of the surface just plotted in its domain. Well, here I've got the gradient vector field superimposed on top of it, and look, this is exactly as we expected a gradient field to behave. If you go anywhere on the contour map, like go to a contour line, the gradient vector is perpendicular to the grid line. And we know that the gradient is always perpendicular to the grid lines because it's pointing towards steepest ascent. Notice that the gradient vectors are all facing outwards. That's because the ascent is to the outside rather than the inside. This is a valley rather than a hill.